welcome to the second part of your sets chapter 2. So today we are going to start with Venn diagrams. A Venn diagram is a pictorial way of representing sets and their relationships using a rectangle for the universal set and circles for the individual sets. So if you see this rectangle here, right, this entire rectangle, it basically represents your universal set, whereas these circles right here, they basically represent your three sets A, B, and C respectively. Right now, basically, when we used to write sets in our set builder form or a roster form, right, we are just basically visualizing that with the help of these diagrams, and this is a pictorial way of representing sets. Okay, so it was introduced by John Venn to visualize set relationships. It represents the universal set. As I told you, the rectangle represents the universal set and ovals represent sets A, B, and C, etc. Overlapping circles show common elements. Separate circles show disjoint sets. So we have already talked about disjoint sets in the last video. Here we are talking about the overlapping circles. So if you can see this part right here, this one which I'm shading, this basically refers to the common elements which belong to A and C both. Right? If I see these elements, they basically refer to the elements which belong to both B and C. And if I talk about this region, this basically refers to the elements which belong to A, B, and C. All the three of them. They're extremely useful for solving problems on unions, intersections, and complements. We're going to see what these terms basically mean. So draw a Venn diagram for A is equal to 1, 2, 3, 4, B is equal to 3, 4, 5, 6 within universal set is given to us from 1 to 8. Okay, let's draw it now. Okay, so this is my A and this is my B. Okay, now I have 1, 2, 3, and 4 and 3, 4, 5, 6. Okay, these are my elements. Okay, so 1, 2, 3, 4. So here 1 and 2 are basically going to lie in this region because they only belong to set A. Whereas 3 and 4 lies both in A and B. So 3 and 4 are going to lie here, right? And 5 and 6 solely belong to B. So therefore, this is going to be our Venn diagram where there are 8 elements in total, right? 1, 2 solely belong to A, 3, 4 belong to both A and B, and 5, 6 belong to only B. Draw a Venn diagram showing three sets A, B, and C that all overlap with one another. We have already done this here. Let us move forward. So the union of sets, which is denoted by A union B. The union of A and B is the set of all elements that belong to A or to B or both. Okay, that basically refers to that all the elements that belong to A or to B or to both. Okay, so definition here it gives that A union B is equal to X such that X belongs to A or X belongs to B. Okay, this symbol basically means belongs. So the elements should belong to A or to B or to both. Okay, now there are certain special cases, right? We have already talked about the reflexive property, right? When we were talking about subsets, that a set is a subset of itself, right? This was the reflexive property. Now there are certain laws when I'm talking about the union of sets. So if you see here that A union A will be A. So this is basically referred to as the idempotent law. Okay, we're going to read about it. Now A union phi is equal to A. Okay, A union universal set is equal to universal set only, right? Okay, now it follows the commutative property. That means that A union B is equal to B union A. Fine. Subset rule, if B is a subset of A, that means, for example, we have taken this. This is A and this circle inside is B. Okay, so if B is a subset of A, then A union B is going to be A only, this entire region, A only. Fine. Now let us solve this example. If A is equal to 1, 2, 3, 4, 5 and B is equal to 4, 5, 6, 7, find A union B. We have to write all the elements which belong in A and B or in both. So let us form a set. Okay, so A union B goes 1, 2, 3, 4, 5, 6, 7. Fine. This is going to be your A union B. Try this question and let me know. Now, intersection of sets, it is denoted by A intersection B. A intersection B basically refers to this area which lies in both A and B, which is common to both A and B. So the intersection of A and B is the set of all elements common to both A and B, right? So here A intersection B basically refers to those elements which belong to A and which belong to B also, which are these elements. Okay, so here in the special cases, if we see, so A intersection A is going to be A only, right? A intersection phi is going to be phi, okay, and A intersection universal set is going to be A. Fine. Again, it is commutative that A intersection B is equal to B intersection A. And if A and B are disjoint, that means that they are non-overlapping. Something like this. So the intersection between them is phi. A intersection B is equal to phi. That means they have no common region. They have no elements which are common to both A and B sets. Okay. Let us solve this example right here. Fine. Let me remove it. So it says that if A is equal to 1, 2, 3, 4, 5 and B is equal to 4, 5, 6, find A intersection B. That means the common elements that lie both in A and B. So here 4 and 5 are common in both the sets, right? So therefore A intersection B is going to be 4, 5. Let us solve this question. If A is equal to 2, 4, 6, 8 and B is equal to 1, 2, 3, 4, find A intersection B. Okay. So here 2 is common and 4 is common. So 2, 4. Let us move ahead. Okay, so now difference of sets, which is A minus B. So the difference of sets A minus B is the set of elements that belong to A but not to B. So the elements that only belong to A but they're not in B. Fine. So if we see this region right here, it also lies in A, right? But it lies in B also. So we have removed this region as well, right? So if we see the definition right here, that X belongs to A, X belongs to A, right? But X does not belong to B. So that is why we are left with only this region and we are going to remove this region. So we are left with only this region. Fine. And we denote it by A intersection B dash. B dash refers to the area which does not belong to B. So B dash refers to this area. Fine. Now it does not follow the commutative property. That means A minus B is not equals to B minus A. And if A and B are disjoint, then A minus B is going to be A only. If we see this, A and B here are disjoint. This is A, this is B, right? So if I'm going to do A minus B, right, then it is going to be A only. If A is a subset of B, then A minus B is going to be phi, okay? If A is a subset of B, that means what I'm trying to say here is that if A is a subset of B, that means A lies here only. So A minus B is going to be phi. There's going to be nothing, right, which belongs to A but not to B. Everything belongs to B here, right? Every element of A belongs to B. So therefore it is going to be phi, right? Let us see the solved example. If A is equal to 1, 2, 3, 4, 5 and B is equal to 4, 5, 6, 7, find A minus B and B minus A. So first of all, let us find A minus B, right? A minus B basically refers to all the elements that belong to A but not to B. So here what all elements belong to B? 4, 5, which are common in A as well. So we are going to remove 4 and 5. So A minus B basically refers to 1, 2 and 3. Okay, and now if you want to find b minus a, then we have seen that 4 and 5 lies in a as well. So we are not going to include 4 and 5. We are just going to write 6 and 7. Fine. These are elements of b, not in a. Let us do this practice question. If a is equal to 2, 4, 6 and b is equal to 1, 3, 7, find a minus b. So I told you these sets are disjoint sets. That basically means that a minus b is equal to a itself. Therefore, it is going to be a is equal to 2, 4, 6. Fine. Let us move forward. Now let us talk about the complement of a set. It is basically denoted by a dash or ac also. If omega is the universal set, right? The complement A dash is the set of all elements of omega that are not in A. So leaving A, what all is left behind in the universal set is your complement of the set A, which is denoted by A dash. So if you see the definition here, X such that X belongs to the universal set and X does not belong to A. That means what are we basically doing here is that we are doing difference of the universal set and our set A. So if we see these key identities here, if I'm going to basically uh, write A union A dash, I'm going to get my universal set because A is this part and A dash basically refers to this part. So ultimately I'm going to get my universal set. If I'm going to do A intersection A dash, so I'm basically going to get 5 because there are no common elements between these two regions. Fine. Now involution, if I'm going to do A dash of dash, okay, I'm going to get A itself. So what do I mean by A dash of dash is that what is A dash first of all, right? So A dash is this area, right? So I'm going to if I'm going to do complement of this area also, then I'm going to get my set A itself. So A dash dash is equal to A. It depends on omega. The complement changes if the universal set changes. Okay, so it just depends upon our universal set only. Okay, remember this. Now, if universal set is equal to 0, 1, 2 till 9 and a is equal to 1, 2, 3, find a dash. So, in order to find a dash, we have to find those elements which are there in the universal set, but they should not belong to a. Right? So if 1, 2 and 3 basically belongs here, what are the rest of the elements that are going to be in the universal set? So they would be 0, 4, 5, 6, 7, 8 and 9. Got it? So this is a practice question right here. Here we are given the universal set to be 1 to 10 and a is equal to 2, 4, 6, 8, 10. Find a dash. So 1, 3, 5, 7 and 9 would be our a dash. Fine? Now commutative law. The commutative law states that the order of sets does not affect the result of union or intersection. So in case of union, if we talk about, so A union B is equal to B union A. And if I'm talking about intersection, then A intersection B is equal to B intersection A. Swapping the two sets in a union or intersection does not change the outcome. The result is going to remain the same. Okay, so the order does not matter when you're doing the intersection or the union. Both union and intersection, but not to the set difference. We already saw that a minus b is not equals to b minus a, right? Similar to a plus b is equal to b plus b, b plus a in ordinary algebra. Now verify the commutative law for a is equal to 1, 2, 3 and b is equal to 2, 3, 4. So let us verify it. Fine. So first of all, I'm going to do A union B. So in order to do A union B, I have to basically take all of the elements of A and B. So 1, 2, 3, 4 are going to be my elements. Okay. Now if I want to do B union A, it is going to be the same, right? 1, 2, 3, 4. So they are equal. Similarly, you could do the intersection also. 2 and 3 elements are going to remain common when you're doing A intersection B or B intersection A. Hence, the law is verified. Verify the commutative law for union using A is equal to 5, 6, 7 and B is equal to 6, 7, 8. So if I want to do A union B, what will I get? 5, 6, 7, 8. If I want to do B union A, what will I get? Again 5, 6, 7, 8. So hence we have verified the commutative law for sets in case of union and intersection. Now let us discuss the associative law. The associative law states that when combining three sets by union or intersection, the grouping does not affect the result. So if I'm writing A union B union C, and if I'm grouping B union C here, and I again write A union B union C, and here I'm grouping A union B. So the result would not be affected. My outcome would not be affected. Similarly, in the intersection, if I write A intersection B intersection C, and here I group B intersection C, it would be equal to A intersection B intersection C. So we may combine any two sets first and the final result stays the same only. Let us see this example. So A is equal to 1, comma 2, B is equal to 2, comma 3, C is equal to 3, comma 4. Verify A union B union C is equal to A union B union C. Right? So first of all, let us solve this. Okay, this part, B union C. So when I'm going to do B union C, what will I get? 2, 3, 4. Right? Now if I'll do A union B union C. So here I have to see A and here I have to see B union C. So I get 1, 2, 3, 4. Similarly, if I do A union B first, okay, this time I'm doing A union B first. So A union B is 1, 2, 3. And now if I'm doing A union B union C, so what will I get? Okay, this was 1, 2, and 3. Sorry. So what will I get? 1, 2, 3, 4. Alright. So both are equal, hence the law is verified. You may try this practice question yourself. It is the same as the solved example. Alright. So now let us come to the distributive law. So the distributive law connects union and intersection similar to the distributive property in ordinary algebra. So if you see this, A union B intersection C. So basically we are multiplying A union with B first and then adding the intersection sign and then multiplying A union by C. Okay, so it goes A union B. Okay, intersection A union C. This is the first form. The second form is this one. Here we are multiplying A intersection, okay, with B first and then applying the union sign and then A intersection C. This is the distributive property. You could compare it with the ordinary algebra analogy, which is A into B plus C is equal to A into B plus A into C, right? Let us solve this example. Okay, so here it says that if A is equal to 1, 2, 3, B is equal to 2, 3, 4, C is equal to 3, 4, 5, verify A intersection B union C. So first of all, let us calculate B union C. Okay, this one. So B union C. What do we get? 2, 3, 4, 5. 2, 3, 4, 5. Alright, now A intersection. Now A is 1, 2, 3 and this is 2, 3, 4, 5. What elements are common? So A intersection B union C, we get, what are the common elements in both B union C and A? 2 and 3 are common. Okay. Now let us solve this part. A intersection B. So when I'm doing A intersection B, what am I getting? 2 and 3, right? When I'm doing A intersection C, what am I getting? A intersection C, only 3, right? Now when I'm doing A intersection B union A intersection C, what am I getting? 2 and 3 and 3 here. So we are going to get 2 and 3, which is the same as this, right? So hence we have proved the distributive law. You could practice this question, okay? Now let us come to the identity law. So the identity law describes how sets behave when combined with the empty set or the universal set. Okay, so when we combine A with phi, that means A union phi, we get A. When I'm doing A intersection phi, I'll get phi. When I'm doing A union universal set, I'll get the universal set. When I'm doing A intersection universal set, I'll get only A. Okay, so 5 behaves like 0 in addition for union and dominates in the intersection. Okay, so here it is basically behaving like a 0, right? So like a plus 0, what do we get? A, right? Here it dominates, okay? So now role of universal set. Universal set dominates in union, okay, and behaves like an identity in intersection. So here it's just an identity. That means it is basically, kind of behaving like 1. If I'm multiplying a by 1, I'll get a. So it is behaving like an identity. Okay, so if we see this example, if a is equal to 1, 2, 3, and universal set is equal to 1, 2, 3, 4, 5, 6, find a union universal set and a intersection 5. We know that a union universal set always dominates in union, so it is going to be universal set itself. So the answer would be 1, 2, 3, 4, 5, 6. All right. And we know that A intersection 5 is 5 itself, which is an empty set, right? Now, if A is equal to ABC, find the value of A intersection 5. What is A intersection? Sorry, A intersection universal set. So it is going to be A itself, right? ABC only. And A union 5. It is going to be A again, which is going to be the same answer. Fine. Now, idempotent law basically states that combining a set with itself by union or intersection gives back the same set. So if I'm combining the same set, okay, A union A, I'm going to get A only. If I am basically doing A intersection A, I would get A only. So the key difference from numbers, unlike ordinary numbers, 2 plus 2 is equal to 4, a set combined with itself does not grow. So A union A is still just A only, right? Here when we add, it basically grows onto a higher number, right? But if I'm talking about an ordinary set, so it does not grow, it is still the same. So A union A is equal to A intersection A is equal to A. So here if A is equal to 2, 4, 6, find A union A, we are going to get this only, right? And A intersection A, we are going to get this only. So it is anyway A only, right? If you see this practice question, if A is equal to X, Y, Z, verify that A intersection A is equal to A. So it is going to be A only, X, Y, Z would be your answer. So now this is a very important law, and this is the De Morgan's law. So De Morgan's law relates the complement of a union. So basically we have taken a union, okay, A union B, and we are basically doing the complement of it, right? Complement of a union or intersection, okay, or an intersection to the intersection or union of the complements. So basically here we are doing the intersection, okay, of the complements, and here we are doing the union of the complements. So this law has to be kept in mind. Okay. So A union B dash. So the complement of the union of A and B is equal to complement of A intersection complement of B, or A intersection B complement is equal to A complement union of B complement. Extremely helpful for simplifying complicated set expressions, right? If we see the solved example right here, it says that if universal set is equal to 0 to 9, A is equal to 1, 2, 3, 4, 5, and B is equal to 4, 5, 6, 7, then we need to verify this, okay? Okay, so first let us calculate A union B. Fine. So A union B here comes out to be 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now, what is the complement of A union B? That means what is left in the universal set which we haven't included here. So it is 0, 8, and 9. Now let us calculate A complement. Okay. So A complement comes out to be 1, 2, 3, 4, 5. So 0, 6, 7, 8, 9. And what is the B complement? So B complement basically comes out to be 0, 1, 2, 3, 8, 9. Now what is common? What is the common element? A intersection B dash. What is the common element? 8 and 9 are common in both. So 8 and 9. Okay, and 0 is also common right here. So 0, 8, 9. So this and this are equal LHS is equal to RHS, hence the law is verified. You may do it same with this practice question as well. Okay, so now let us see where these sets are basically applied in practical life, right? So set theory is the foundational language used across many branches of mathematics, statistics, computer science, and everyday reasoning. So mathematics is basically, in mathematics, it is basically used to define relations, right? Define relations, functions, and sequences. In probability and statistics, the sample space of an experiment is treated as a set. In computer science, databases and search engines rely on set operations, union or intersection. And in surveys and businesses, Venn diagrams and cardinality, they solve overlapping group problems in market research. So if we see this example right here, in a survey of 300 companies, so our universal set is 300, 200 use newspapers, right? So 200 of them are basically using newspapers, 100 use radios. So n of n, that means the number of people who are using newspapers is 100. Okay, number of people who use the radio is 100 and 50 use both. Okay, so that means n of n intersection r is equal to 50. Find the number using newspapers or radio. Wherever you see this word or, that basically means that you need to find A union B. Now we have already talked about that A union B is equal to n of A, right? So n of A union B is equal to n of A plus n of B minus n of A intersection B. Okay, similarly, we are going to just place all of our values here, right? This was 100. This was also 100. And n of n intersection r was 50. So what we will get? 200. Okay, so this is 200. So 200 plus 100 minus 50. So this is going to be 250. Fine. So 250 companies use both newspapers or radios. Okay, so these are some real life examples of sets. So sets are all around us. So many everyday collections become mathematical sets once we define them clearly. So days of the week, fruits in a basket, students present today, colors of a rainbow. So they can be considered as sets, right? If you see this example right here, write the set of months of the year having exactly 30 days. So they are April, June, September, November, right? You may try this also once. Okay, I have some questions for you as well for practice, which you can try. Right, so these are certain questions which you can try. Okay, and we would be solving these questions in the next video. Right, you may try them, and yeah, we would try them in the next video. So thank you everyone. This was all for sets chapter. Right, thank you so much. Take care and bye.